The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI Conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI Conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
Our first presenter today will be Professor Doug Hooton. Doug is the NSERT CAC Industrial Research Chair in Concrete Durability and Sustainability in the Department of Civil Engineering at University of Toronto. He's a Fellow of the ACI and ASTM and the Engineering Institute of Canada. He's received the Award of Merit from both the Canadian Standards Association, CSA, and ASTM. He is or has recently been chair of several CSA, ACI, and ASTM standards committees related to cement and concrete. And today Doug is going to be talking to us about evaluating concretes using rapid resistivity measurements for fluid penetration resistance. Yeah, you can use that or you can use those.
That's right. And I apologize to my co-author, Ahmet Sharudi. It's National East Concrete, not Northeast. I did this late. Actually, early this morning, I prepared these slides. And he also does doing some work with Geotech Scientific, so I acknowledge that. Co-authors. Ahmad did his master's with me a couple of years back, and Esther Parker, who's now with Lafarge, was also a master's student with me at Toronto. And one of the reasons we need these rapid test methods is because typically the durability problems that we face are related to ingress of water and resistance to ingress of water or solutions carried in water or other. So if we can control the rate of fluid ingress, we can improve the durability of concrete and try and prevent some of these interesting premature degradations. Okay. So, hello? Sorry. Okay, well, I'll try and do that. So I'll probably look at the screen, so maybe I should stand like this. Okay, so some 10 or 15 years ago, I formed a subcommittee at ASTM on methods for measuring fluid ingress, or subcommittee 966, and we've developed several standards, one of them being the C1556, which is a chloride bulk diffusion test based on the Scandinavian method, 1585 on rate of absorption. We already had the C1202 rapid chloride permeability test, which predated the committee. And just in the last 6 months, we've standardized 1760, which is a quick bulk electric conductivity test based on using the 1202 equipment. Where you take a 1-minute measurement and just take the current and measure conductivity, and conductivity being the inverse of resistivity. Sort of leads us where I'm going with this talk. And we're also looking at several resistivity methods, and we're looking at a rapid absorption method. We summarized some of this about 2 years ago in Concrete International. I worked with Steve Lane and Rachel Detweiler. We wrote a paper discussing some of the various transport mechanisms and how they're measured, and talking about ASTM methods and other methods as well. And one of the things that's been going in Canada, we have performance specifications for concrete in Canada, largely. And one of the things, of course, with performance specifications is you need to be able to measure performance. So we need accurate and precise standard test methods that can be used to measure things like chloride penetration resistance or any fluid penetration resistance in concrete. They need to be simple, they need to be rapid, but still relate to the performance, and we need appropriate acceptance limits to include in those performance specifications. And we need rapid methods. I mention this because a number of high-profile 100-year service life projects have used chloride bulk diffusion testing for pre-qualification on projects, but then some of them have tried to use similar testing for construction acceptance. And it's just inappropriate to have a test method that takes you almost 6 months to complete as an acceptance test on construction. It's great for if you've got a time on a major project for pre-qualification and for implementing service-like modeling to see if you're going to achieve your service-like model, because typically diffusion is one of the input parameters. But for construction acceptance, it's completely impractical because it's just too slow for use. So we need rapid test methods that can be used that are practical for quality control. Now, the one that has been used around the world in a number of places is the ASTM C1202 test. And it's been criticized, and I'm going to go through these things. There's the NT Build Rapid Migration Test developed by Tang and Ping in Sweden. It's been standardized for more than 10 years now, and that's an interesting test too. But then we can look at some of the resistivity tests, either bulk conduct or resistivity tests or surface resistivity tests. A lot of work on that. The difference it's all relative what rapid means. Typically, ASTM C1202 and the Nordtest method, you're typically looking at 2 days to complete the test. By the time you prepare the sample, precondition the sample, and run the test, you're looking at 2 days. Whereas these resistivity test methods, you're looking at in the order of 1 minute to do the test. So the sample preparation isn't the same. The test method is relatively rapid, and so there's a lot of advantages to these bulk resistivity tests. These other tests, I think, make good interim test methods on our way to rapid test methods, but if we can make the link to performance, these really rapid test methods will go a long way to make them more useful in a number of specifications. So the rapid chloride permeability test, as you all know, it was developed by Dave Whiting back in the early 80s as a rapid test relative to the 90-day ponding test the highway departments were using back then. So it was rapid on a relative scale of rapid. And it has a salt solution on one side, a hydroxide solution on the other side, and you pass voltage through it, a fairly high voltage. He picked 60 volts because that was the highest voltage you could use without electrocuting your technician under the electric safety code. And he picked 6 hours, so it fit into a working day. So you could set it up, run it, and finish the test in 8 hours. So you wonder why some of these things come from, but that's the practicality of where that test came from. And if Dave Whiting was alive today, he wouldn't design this test method with all the knowledge we've gained since 1980 with these sorts of test methods. But it exists, and a number of agencies use it. A number of testing agencies use it. Highway agencies use it. It basically measures electric current flow through concrete. And the analogy is you'll get more current flow through higher porosity systems, and systems with bigger pores, more connected pores, you're going to get higher current flow. If you're more tortuous, fine pore network, you get less current flow. However, there's a couple of shortcomings in this test method, one of them being the influence of pore solution conductivity to carry the current, and one is due to heating that occurs at 60 volts over 6 hours that you can get in high current flow systems. Heat buildup and conductivity is very sensitive to temperature. So as the temperature goes up, the conductivity accelerates or increases rapidly. So there's ways of getting around the thing, and the temperature issue is by taking a shorter term just current value and doing it 1 minute, which is the 1760 concept. You get rid of the heating problem. And we've written some caveats in 1202 about conductivity issues with different admixtures that have a big effect on pore fluid conductivity. Okay, we did some tests. You don't need chlorides in this test to do it. You can use sodium hydroxide on both sides. You get exactly the same current charge in coulombs, and with 2 types of concrete here, we often joke that you could probably use beer. We found out that wasn't true. That you get much different numbers if you use beer as your conductive fluids. You're just connecting your electrodes to the concrete. So don't use beer as an electrolyte. It's a lesson there. The reason for that is that the electrical conductivity of beer is much lower than chloride solutions or hydroxide solutions. So there are differences in the conductivity between hydroxide and chloride solutions, but they're similar enough that it doesn't affect the outcome of the test. But a low conductivity fluid doesn't work so well, so don't try that at home. Okay, so we have this test method. A number of agencies use it, and we have it written into the Canadian standard for certain durability classifications. But it's an awkward conductivity test. And as I said, conductivity is just inverse of resistivity, so why don't we just measure resistivity to get the same answer and do it quicker? It does relate, rapid chlorides. Melissa Titherington did some work, she's here, we can relate that to bulk diffusion measurements. You do get a reasonable relationship we've related to water permeability, Michelle Knockins' work, charge pass and water permeability. So you can relate it to all these sort of things that we're interested in terms of performance. I mentioned the Nordtest method, the rapid migration test that Tang Luping developed, and it's a similar setup. I mean, the physical setup's different. Use a Volvo radiator tube, a 4-inch radiator tube instead of a couple of cells, and you create a seal around your sample, and you put hydroxide on one side, chloride on the other. It looks a lot like a rapid chloride test, but you're not measuring the current flow now. You actually measure the chloride ingress. At the end of the test, after a fixed period, you split it open, you spray it with silver nitrate, and you get a visual cue, because silver nitrate, when it hits chloride in solution, turns to silver chloride and precipitates out as a white precipitate. That's why you see that white designation or delineation there. And silver nitrate, on exposure to light, turns brown. It's black and white photography on concrete. And so you get a visual impression of that depth of chloride ingress. You average that ingress, and you can fit that to a non-steady state diffusion equation and actually get a diffusion coefficient out of this. And this test is being used, I think it's being used as a spec limit on the new bridge going between Germany and Denmark as a quality control test. But it still takes in the order of 10 to 48 hours to do this test. So it's still not an easy test. It's relatively simple to prepare, but it still takes time. A bulk resistivity method, on the other hand, just simply you put 2 electrodes on some sort of transfer wet sponges and measure the current flow through a cylinder of known geometry, and you can calculate the resistivity by the resistance you measure times the area divided by the length. It's relatively simple. You can take a 4x8 cylinder or a 6x12 cylinder, and you can measure the bulk resistivity, and you can take the same cylinder a minute later and put it in a testing machine and test it for strength. So the advantage of that type of test is you don't even have to cast extra specimens to measure something in addition to strength that has an indicator of performance or durability. And a number of commercial pieces of equipment are now available to measure this sort of property. And I'll mention a couple of them just because I've got them in the lab and using them, not plugging them in particular, but we have the equipment, we're using some. The German has their Merlin equipment, and I think he's got it down on the display here. And it's just, again, 2 sponges, electrode, just squash it in between. He's got a nice computer interface that measures the resistivity. And you can relate that, that's coulombs on the left of that axis and resistivity on the right in ohm meters, and you get a reasonably good fit of the data. It's nonlinear, it's sort of x to the -1 relationship. We could have plotted it differently to give it a straight line. But it uses a fixed frequency, as I've shown there. And I think I've got that correct. It's pretty close. Now, also down in the display, you can see another piece of equipment by Geotech, their RCon device, and they use a variable frequency. They would do a frequency sweep and measure over a range of frequencies and pick a resistivity where they reduce the impedance effects, because resistivity is more complicated than you might think in terms of there's high frequency and low frequency arcs, and you want to pick one where the line intercepts the axis where you've the impedance effects are reduced. And so from a scientific point of view, this seems to make a lot of sense. And if you relate that, so you can do this thing and pick the optimum frequency, and you can do this and measure it with the Merlin with a fixed frequency, and you get a linear relationship, but the slope isn't 1, which means you get different answers. But they relate to each other. So there's the problem we have right now. I'm trying to standardize a test method for Canadian standards, and I'm trying to do the same thing at ASTM. And we've got a problem is we've got different pieces of equipment that give similar sounding numbers, but they're different. So how do you develop test method limits for something where you get different numbers with different equipment? If you're using one piece of equipment, you can relate it to concrete quality, and all this data points are different water cement ratios, a whole range of cementing materials that we just did over the summer to look at it. And we tried changing the frequency. That was last slope was 1.2 approximately, 20% difference in the result. When we used a 1 kilohertz fixed frequency on the one device, we dropped that to a 7% for the relationship. So that's one of the problems I'm facing now, and I'm trying to deal with that in the next 2 weeks for the Canadian standard to get something in our next ballot. Is how do we define a test method that deals with this difference, or do we design different limits for different test methods? And of course, the highway departments have been having fun Started with Florida DOT and Louisiana DOT, and now it's national standard. They've been pushing this 4-point Wenner Probe surface resistivity, where you've got 4 points. It's shown schematically on the right, where you apply a voltage through the middle and you measure the current out of the outer 2 electrodes, and you calculate a resistivity based on that equation, based on the geometry. And again, you use some pressure-related spring-loaded things in this particular device with wet electrodes. And you relate that again, a similar x to the -1 relationship of surface resistivity versus the 1202 data. So very similar to what I showed before with the bulk resistivity and charge passed. And we can use these things, like here's a surface resistivity. We did some studies, part of Ahmad's work, with 3 groups of concretes. We have sort of high-performance concretes with silica fume and slag, and the top 3 curves are there, but the difference between the 3 curves there are different water cement ratios. If water gets added on site, you can see the resistivity drop as the water is added. And we see the same thing with some straight slag mixes, and down at the bottom with some Portland cement mixes. So it is sensitive to small changes in water cement ratio, and it is very sensitive to different cementing materials, because supplementary materials typically increase the tortuosity of the pore structure so that you get higher resistivities. Okay. Now, but the trouble with the surface probe, the way the highway guys have done it, is they basically fixed the probe spacing between these 4 probes. But you're making some assumptions, because the equations are developed for electrodes in contact with a semi-infinite mass of concrete. But so the geometry impact, when you don't have that, the geometry of the test or the thing you're examining is affected by the probe spacing. And Steve Millard in the UK did some work over 20 years ago on this, looking at how you would adjust probe spacing to get optimum probe spacing for different size and different shape samples. And when you do this, for example, I'll just pick one of the bulk resistivity methods versus the Wenner probe on the vertical axis, we get the same answer. The slope is effectively 1, so we get the same answer from the 4-point surface probe. When you optimize the spacing, these are 4x8 cylinders with 1-inch spacing, it works. You get the same answer. We change to 50-millimeter spacing, the slope becomes 2. Because it's not inappropriate spacing for that size cylinder. So you don't get the same answer unless you adjust your probe spacing for the geometry of the sample you're measuring. So you'd use a different geometry for a 6x12. Okay. Then we look at Wenner probe spacing again versus the 1202, or the 1-minute or 5-minute values, which is effectively 1760, the ASTM test method. We get a slope of 1.5. So again, it's not the same answer. Good relationship, but not the same answer. So that's the problem we're having with a number of these test methods. Now, Jason Weiss did a lot of work for the highway group on doing the Wenner probe, because the highway departments have been keen on this Wenner probe device. And he actually developed what I call a hot-wired version of it, where you put jumper cables on the 4 probes and run it to 2 plates, and basically you measure bulk resistivity from end to end on those 2 steel plates on the ends. And when he does that, he gets the same number. So there's the direct AC from the bulk resistivity using the same hot-wired version versus the bulk resistivity from one of the commercial devices. So we're getting the same slope. And AASHTO, in their wisdom, with this new surface resistivity test method that they've developed, has come up with some equivalencies to what the C1202 Coulomb values are based on that test method, some relative rankings that have been in there at that test from the beginning. And so they've come up with some ranges of saturated electrical resistivity that would relate to those values. Some of our data with some of the other equipment would give us different numbers than what they've got with that table there. And of course, the other thing with resistivity, it's very sensitive to saturation. Your sample's got to be absolutely saturated, but surface dry. You don't want to short out around the edges. You want to have, but you want all the pores fully saturated when you do the test. So this is our dilemma. The fixed frequency, low frequency typically, bulk resistivity devices give the same value as one of the other devices, the 4-point Wenner probe when it's hot-wired or not hot-wired, and but not the same as the 1760 value gives you if you convert conductivity into resistivity. And the variable frequency devices, the more sophisticated devices like the RCon or the Solartron equipment, at least Jason Weiss at Purdue has evaluated the Solartron as well, they give very similar values when you sweep through the frequencies and pick an optimum. But they don't agree with each other in terms of an absolute number. They relate to each other, but they don't give the same number. So my dilemma is, how do I write this down as a standard test method when we get different results depending on how we specify the test method, when there's commercial devices going both ways? So that's my dilemma, and I'm looking for help very quickly, too. We've got a few weeks, and this is what we'd like to have, but we don't have it. So I think that's the end of my talk.
Okay.